In 2015, humanity heard something it had never heard before, a sound from deep space that proved black holes were real, violent, and far closer to us than we ever imagined. For most of modern history, black holes were considered mathematical curiosities, not physical objects. They emerged naturally from Albert Einstein's theory of general relativity in 1915, but the idea seemed absurd. A region of space where gravity becomes so strong that nothing escapes, not even light, felt more like a flaw in the equations than a feature of reality. Even Einstein himself believed the universe would never allow such objects to exist. For decades, black holes remained theoretical. Astronomers could not see them. They emitted no light. There was no direct evidence of their existence. And yet, nature kept offering subtle hints. Stars were observed orbiting invisible masses at incredible speeds. Powerful X-ray emissions appeared to come from empty regions of space. Something unseen was influencing the cosmos. Still, doubt remained. Everything changed on September 14, 2015. On that day, two identical instruments located thousands of kilometers apart, one in Louisiana, one in Washington state, detected a signal so faint it lasted less than a second. The instruments belonged to LIGO, the Laser Interferometer Gravitational Wave Observatory. They were designed to detect gravitational waves, ripples in space-time predicted by Einstein exactly 100 years earlier. The signal was unlike anything ever recorded. It was short, it was clean, and it matched a prediction that many scientists never expected to confirm. Two black holes had collided. These black holes were not small. Each was dozens of times more massive than our sun. They spiraled toward each other at nearly the speed of light, merging in a fraction of a second. In that instant, more energy was released than all the stars in the observable universe combined, and Earth felt it. Not as sound, not as light, but as a tiny distortion in space-time itself, smaller than the widths of a proton. For the first time in history, humanity did not see a black hole, we heard one. This single detection changed black holes from theoretical possibilities into directly observed physical objects, but it also created a new problem. The black holes detected by LIGO were larger than expected. According to existing models of stellar evolution, stars massive enough to produce such black holes should not exist in the modern universe. Once again, black holes were breaking the rules. According to astrophysics, black holes form when massive stars die. A star survives by balancing gravity pulling inward with nuclear fusion pushing outward. When fusion stops, gravity wins. The core collapses. If it is heavy enough, it becomes a black hole. But there are limits. Stars above a certain mass should self-destruct completely in a process called pair instability. Instead of collapsing, they explode so violently that nothing remains. No neutron star, no black hole, just scattered matter. Yet LIGO detected black holes sitting precisely in this forbidden range, and it was not a one-time event. As more gravitational wave detections followed, a pattern emerged. Black holes were merging with masses that should not exist. Some appeared to have formed surprisingly early in the universe's history, when there had not been enough time for stars to grow, die, and collapse. The universe was telling us something was wrong with our assumptions. One explanation suggests that these black holes were not formed from single stars. Instead, they may be the product of earlier black hole mergers, second-generation black holes, growing larger with each collision. Another idea proposes that stars in the early universe behaved differently, forming under conditions unlike anything we observe today. But there is a deeper implication. Gravitational waves gave scientists a new way to study black holes, not by observing light, but by listening to space-time itself. This allowed physicists to test general relativity under extreme conditions. So far, Einstein's theory has passed every test. But black holes remain a place where general relativity and quantum mechanics collide and fail to agree. At the center of every black hole lies a singularity, a point where density becomes infinite and the laws of physics break down. General relativity predicts this. Quantum mechanics rejects it. Information, according to quantum theory, can never be destroyed, but black holes appear to erase information completely. This contradiction is known as the black hole information paradox, and it remains unresolved. Gravitational waves did not solve this paradox, but they confirmed something more unsettling. Black holes are not rare. They are not exotic. They are a natural outcome of how the universe evolves. Every galaxy is shaped by them. Every cosmic structure feels their influence. The Milky Way itself contains a supermassive black hole at its center, 4 million times the mass of the Sun. It is quiet now, but its gravity controls the motion of billions of stars. Black holes are no longer theoretical monsters hidden in equations. They are active participants in the story of the universe. And yet, the more we learn about them, the more they challenge our understanding of reality. The first gravitational wave detection was not just proof of black holes, it was proof that the universe still operates beyond the limits of our intuition. Space is not a passive stage. Time is not fixed. Reality itself can stretch, ripple, and vibrate. Black holes force us to confront a humbling truth. The laws of physics we rely on work, but only within limits. Beyond those limits, the universe plays by rules we have not yet discovered. And black holes sit precisely at that boundary. Somewhere in the universe, right now, black holes are colliding, warping space-time, and sending silent signals across the cosmos, signals that may reach Earth long after humanity is gone. They do not announce themselves, they do not explain themselves, they simply exist. And as long as they do, they remind us that the universe is still full of mysteries, powerful enough to change everything we think we know. If you want more real stories from deep space, subscribe to the channel. And tell me in the comments, do black holes reveal the limits of physics or the future of it?